Welcome back. So again, I was just talking about how when we're looking at the graph, we want to be able to understand that we're just trying to represent that lowest potential energy for how we are determining the bond length. So with our bond length, let's define this now. What is a bond length? You have this blank in your guided notes. A bond length is the distance between two bonded atoms at their minimum, potential energy. Bond length, the distance between two bonded atoms at their minimum potential energy. So one of the things that we could say is, again, as these bonds are forming, the bond length is more like that Goldilocks zone, although there are some other positions as these bonds are about to form and as they are maybe getting too close. But we would take the lowest energy as the bond length. These are all going to be provided for us in some very nice tables from very fine chemists that have come before us and done a lot of work for us. One of the misconceptions I wanted to make sure that we describe is that, shared bonds and covalent bonding allow for the sharing of an electron in an area of probable space. Models illustrate bonds as lines or sticks for simplicity. In reality, the bond is more like a new type of orbital, and we describe this as a molecular orbital. So again, the electrons are increasing their probability in being between these two atoms. We're going to see that as like a line between two chemical symbols, like we could say hydrogen dash. Hydrogen would represent to us two hydrogen atoms bonded to each other. All right. I also wanted to say bond length is an average measurement. We understand that electron clouds are fuzzy. Electrons are in constant motion. So these atoms, when they're forming this bond in that Goldilocks zone, they kind of wiggle back and forth the whole time. They don't really stay in one position. They are constantly in motion. So they kind of wiggle back and forth. And that, again, this is because of the constant movement of electrons. So in your guided notes, there's this little blank. You have a little arrow for it. Why is it that bond length is just an average measurement? This is because the constant movement of electrons. They are constantly moving. So we just average it. Moving right along here, bond energy. What is bond energy? Bond energy is the energy required to break a bond. So bond energy, the energy required to break a bond. The reason why this is important is because when we are breaking a chemical bond or when a bond is forming, which is going to be the opposite, it's going to release energy, we understand that this is abiding by the law of conservation of energy. We actually have that as our next blank. So this is allowing us to say, hey, if forming a hydrogen bond, a bond between two hydrogen atoms, releases whatever the units of energy are, I don't know, some 410 units of energy, we can reason that if we needed to do that chemical process or if we needed to do the reverse chemical process, it would be the equal but opposite amount of energy. So this is just some understanding of the law of conservation of energy. All right, our next directional arrow, bonds with the strongest bond energies usually involve elements hydrogen or fluorine. So you can have H or F. So this is particularly for covalent. So for covalent bonds, things that have the strongest bond energies typically have hydrogen or fluorine. We're going to talk about this on Monday when we delve a little bit more into electronegativity, because fluorine is going to be the most electronegative atom. But one of the things that we'll talk about with these atoms is they have some extremes. So fluorine is going to be an extreme in that it's the most electronegative. Hydrogen is going to be an extreme in that it is the smallest atom that we can work with. Stronger bonds generally have shorter bond lengths. So this will be our last blank for today. We will continue on page 3 on Monday. But stronger bonds generally have shorter bond lengths. So I want you guys to think about this and the energy that it would take to require to break these, like breaking sticks out in the wood. So, for example, if you are making a bonfire or if you are pulling kindling in to make a fire in your fireplace, maybe you've experienced this. If you have a really long piece of wood and you have a really short piece of wood, usually in class I hold up a pencil and my meter stick. Or maybe a couple different, I don't know. I have one pencil that's like whittled all the way down to the eraser. I would hold that one up. But anyways, if you have two pieces of wood and you're trying to break one, and it is, let's say, a really long piece of wood, you can bend it over your knee. You can use the force and snap it pretty easily. If you have a really, really short piece of wood, and it is the same diameter, we have to have some controls here. Maybe it isn't the best example if this takes too long for me to say. Anyways, if you have a shorter piece of wood, you're not going to be able to sort of bend it over your knee. You're not going to be able to snap it as easily. All right. It's a better example when I have a visual example. It's not so great when I'm trying to describe it, especially if nobody plays in the woods anymore. All right. Anyways, guys, this is the end of our page 2 of our guided notes. Again, make sure you did the warm up today and then you'll be all set. And check in again on Monday. We are going to continue our guided notes and I'll have you do some practice with some electronegativity work. All right. Have a good weekend.